we're going to continue our review of factoring methods. In this section, we're going to focus on factoring binomials. Now, there will be three different kinds of binomials that we will factor. First, we'll focus on factoring a difference of two squares, and then we'll move to a sum of two cubes and a difference of two cubes. To get us started and to understand how to factor a difference of two squares, I want you to consider multiplying these two binomials. Now, I hope we feel comfortable distributing. So n times n times negative 9, 9 times n, and 9 times negative 9. When we distribute, we get n squared negative 9n plus 9n minus 81. And you can see that these two terms are opposites, so they cancel, leaving you with just n squared minus 81. This is a difference of two squares. So let's work backwards. If I give you a difference of two squares, this is a difference because it's a subtraction. This is a perfect square. And 81 is a perfect square. It's 9 times 9. How does it factor? Well, look at how it factored in the beginning. N plus 9, n minus 9. So watch this. If this is n squared, then an n goes there, and n goes there. And 81, what number squared gives you 81? 9. So 9 goes there, and 9 goes there. And notice that the signs are opposites. So here we go, guys. Here is the pattern that we will follow. If I give you this perfect square, a squared, and then minus this perfect square here, b squared, this is a difference of two squares. It will factor as a product of two binomials. One will be plus, the other one will be minus. And then what we'll put first here is the term whose square gives you a squared. Well, that would be a. And then second, I will put the terms whose square gives me b squared. That will be b. So this is the pattern that you and I will follow whenever we want to factor a difference of two squares. Check out this first example. Is it a difference of two squares? Well, first of all, it's a difference. There's a minus sign right in the middle. Is 25x squared a perfect square? Yes, it is, because it's 5x times 5x. Is 36 a perfect square? Yes, because it's 6 times 6. So this is definitely a difference of two squares. It will factor in this pattern, following that pattern. So let's go for it. It will factor as a product of binomials, right? One will be plus, and the other one will be minus. What do you square to get 25x squared? 5x. So then 5x goes there and there. What do you square to get 36? 6. So 6 goes there and there. This is the factorization for that difference of two squares. Next example. First of all, this is a difference. 49x squared is 7x times 7x. 81y to the fourth is 9y squared times 9y squared. Therefore, this is definitely a difference of two squares. It will factor in this pattern, or following this pattern. Here we go, guys. Okay, so it's going to factor as a product of two binomials. One will be plus, the other one will be minus. What do you square in order to get 49x squared? 7x. So 7x goes first. What do you square in order to get 81y to the fourth? 9y squared. So 9y squared goes there, and you are done. Again, if you want to check, if ever you want to check your factorization, you can distribute, and you should get the original binomial back. After careful consideration, you will see that this is indeed a difference of two perfect squares, so we will factor it as such. Let me set up my binomials. I'll put a plus sign in one, making sure they have opposite signs. Now, I would have to square x squared in order to get x to the fourth, right? X squared times x squared gives me x to the fourth. So I'm going to put x squared here and x squared here. 4 times 4 gives me 16. 4 squared is 16, so I put 4 there and there. This example is so important, you guys, because unlike the other examples, you're not done right now. And you're not done because you have not completely factored. I can see that I still have a difference of two perfect squares right here. It's a difference, and both x squared and 4 are perfect squares. So this is still a difference of two squares, so I should continue to factor. This, however, is not a difference of two squares, it's a sum of two squares. And a sum of two squares never, ever factors. A sum of two squares is prime, so do not factor this binomial any further. So what I'll do is I'll just copy down the sum of two squares. That part is done, but this is still a difference of two squares, so I will follow the pattern for factoring it as such. All right, here we go. So we know that the signs are opposites, and what do you square to get x squared? X. X squared gives you x squared, right? X times x gives you x squared. What do you square to get 4? 2. So then 2 goes there and there. Now, a careful look will tell you that you no longer have, a careful look will reveal that you no longer have a difference of two squares. So you are completely factored at that point. So the rule here is, or what you want to keep in mind, is that you want to make sure that you have completely factored. So once you factor once or even twice, check out each factor in the factorization and ask yourself, can that factor be factored further? Okay. Now check out this example, number 5. It says 5x to the fourth power minus 405. Now when you first look at this, you see, oh, I have a binomial. So immediately I think, oh, it's a difference. But is it a difference of two squares? Well, not the way it's written right now, because 405 is not a perfect square. Neither is 5, by the way. But you know what? The first step of any factoring problem is the GCF. So let's actually first factor out the GCF. Maybe after we factor out the GCF, then we'll have something that looks like a difference of two squares. Maybe we'll have something that factors, all right? So the GCF here is 5, right? 5 goes into the first term and the second term. When you factor out 5 from each term, you get x to the fourth power minus 81, right? 5 goes into 40 80 times. 5 goes into 48 times. 5 goes into itself once. All right, now that you factored out the GCF, notice, oh, now this is a difference of two squares. So now I can factor this in here as a difference of two squares. What do I do with the 5? Just bring it along with you. Goes for a free ride, if you will. All right, here we go. Set of binomials, opposite signs. What do you square in order to get x to the fourth? If you said x squared, you're correct. What do you square to get 81? If you said 9, you're correct. Now, you have factored once right here when you factored out the 5. You have factored twice now when you factored it as a difference of two squares. Are you done? Well, this is a sum of two squares, so that doesn't go anywhere. That doesn't factor at all. But this is a difference of two squares, so this binomial factors further. So I'm actually going to have a third step of factoring here. So let's keep going. Copy down the 5. Copy down the sum of two squares. But the difference of two squares, if I can fit it in here, factors further. So opposite signs. And then what do you square to get x squared? If you said x, you're correct. And then you would have to square 3 in order to get 9. Now, if you take a careful look at every single factor, you will see that you no longer have a difference of two squares anywhere in the factorization. So now you're done. So please don't forget what you learned in the previous lesson, which is factoring out the GCF should always be done first. All right, so what we're going to do now is shift our attention to factoring a sum of two cubes and factoring a difference of two cubes. To lay down the foundation for that pattern, I want us to first consider multiplying these two polynomials. The first polynomial, the first factor, is a binomial. The second factor is a trinomial. All right, so to multiply, we will distribute a times a squared, a times negative 2a, a times 4. I'm going to go ahead and write down right now what I get. A times a squared is a cubed. A times negative 2a is negative 2a squared. A times 4 is positive 4a. Next, I will distribute the 2. So 2 times a squared, 2 times negative 2a, and 2 times 4. So 2 times a squared is positive 2a squared. I'm going to go ahead and stack up the like terms. 2 times negative 2a is negative 4a, and 2 times 4 is 8. All right, and I will consider now combining like terms. These cancel and those cancel, leaving you with, watch this, a cubed plus 8. This is a sum of two cubes. So that's great. A cubed is a perfect cube because it's a times a times a. 8 is a perfect cube because it's 2 times 2 times 2. So the question is, how does a sum of two cubes factor? Well, it's up here. Notice it factors as a binomial followed by a trinomial, and I want you to notice the pattern. See this plus sign? That's the same sign in the first factor. In the binomial factor, it has the same sign. Notice this first sign in the trinomial factor. It's the opposite sign. See, this is plus, that's minus, that's opposite, right? And then here, this is a positive. I wonder if that's always the case. Keep that pattern in mind. Let me show you something else. All right, one more time, I want you to consider multiplying these two factors, okay? Again, notice that it's a binomial followed by a trinomial, right? Okay, so let's distribute. P times p squared is p cubed. P times 3p is 3p squared. And p times 9 is 9p. Now distributing the negative 3, right, gives me negative 3p squared. It gives me negative 9p, and it gives me negative 27. Notice that these terms are opposite, and so you're left with p cubed minus 27. This is a difference of two perfect cubes. This is a difference. P cubed is a perfect cube because it's p cubed. It's p times p times p. 27 is a perfect cube because it's 3 cubed. It's 3 times 3 times 3. So the question is, how does it factor? Well, it's up here. It was already factored in the beginning. Notice the pattern. It's the same pattern as what I just finished showing you. It's a binomial followed by a trinomial. Notice the signs. Minus, minus. So it's the same sign. The next sign is the opposite sign. And then this last term is positive. In the previous example, I showed you that the last term was positive as well. So it seems like the last term is always positive. All right, everybody, here's the pattern. So I have a sum of two cubes first, okay? It will factor as a binomial followed by a trinomial. The sign will be the same sign, opposite sign, and this last term is always positive. This first term will be the term whose third power, whose cube, gives me a cubed. In other words, let me say that maybe a little more clear. What do you cube in order to get a cubed? A. So this is going to be A. Okay. I can get that. All right, there we go. And then the next term is, what do you cube in order to get b cubed? B. If you cube a, you get a cubed. If you cube b, you get b cubed. Now this first term will be the square of a, so a squared. This middle term will be the product of these two terms. A times b is ab. And then the last term will be the square of your second term here in the binomial factor. So b squared. This is the pattern that you want to follow when you are factoring a sum of two cubes. Now, what about a difference of two cubes? Well, it's the same exact pattern. The only thing that's different are the signs. I would invite you here to pause the video and try to factor a cubed minus b cubed as a difference of two cubes, following this pattern. All right, so I hope you did that, and I hope you factored it as a minus b times a squared plus ab plus b squared. All right, so this is the pattern that we're going to follow for factoring either a sum of two cubes or a difference of two cubes. All right, everybody, this is a sum, right? Well, let me actually go back a little bit. This is a binomial. It's two terms, right? So I see a sum here. So the only way this binomial will factor, this sum will factor, is if this happens to be a sum of two cubes. All right? Because remember, a sum of two squares does not factor. So the only way this is going to factor is if it turns out to be a sum of two cubes. Let's check it out. It's definitely a sum. X cubed is a perfect cube, and then 125 is also a perfect cube. It's 5 times 5 times 5. So then I can factor this as a sum of two cubes, and this is how it will factor. This is the pattern. So let's go for it right now, shall we? All right, here we go. First of all, the first factor will be a binomial. The next one will be a trinomial. I will have the same sign, opposite sign, and then always positive. Some people use this acronym called SOAP. Here, let me show it to you now. SOAP, this acronym sometimes helps some students remember what the signs are when factoring a sum or a difference of two cubes, okay? So SOAP, the S stands for same sign. O stands for opposite sign. That's the second sign. It's opposite. And then the last sign here is always positive. If you find that helpful, then go ahead and use it. All right, we're back to our problem. And I'm following this pattern right here, everybody. I already have my signs. And so now I think about, what do I cube in order to get x cubed? X. What do I cube in order to get 125? 5. And then this, I'm following this pattern here. This first term is, look at a squared. This first term is the square of x. So that's x squared. This middle term, a times b. Okay, so this middle term will be the product of x and 5, 5x. This last term, b squared, so this last term will be the square of 5, the square of 5. There you have it. This is the factorization for this sum of two cubes. This is a good example. It's a binomial, and so I also noticed that not only is it a binomial, but it's a difference. So your only option, or your only possibility of this factoring, is if this is either a difference of two perfect squares or a difference of two cubes. Now I can tell right away that this is not a difference of two squares because x cubed is not a perfect square. Neither is 27, all right? So the only way that this will factor is if it's a difference of two perfect cubes. And it is a difference of two cubes, and I'll walk you through that right now. All right, it's a difference of two cubes. I will follow the pattern for factoring a difference of two perfect cubes. All right, everybody? It's right here. Here we go. All right, here is a binomial, and here is a trinomial. Do you remember SOAP? SOAP says same sign, right? It's the same sign as they gave me, right? Same sign, and then opposite sign, and then always positive. Now be careful here. What do you have to cube in order to get 1,000 x cubed? So allow me to please kind of walk you through this a little bit here, if I can get some more space. I'm asking you this question. What do you cube in order to get 1,000 x cubed? And the answer there is 10x. If you cube 10x, you will get 1,000 x cubed. What I'm saying is, if you let this be 10x, 10 cubed is 10 times 10 times 10, which is 1,000, and then x cubed, of course, is x cubed. So then 10x is the first term that goes here. All right. Next, what do you have to cube in order to get 27y to the 6th? Now, I don't know if that comes to you right away or not, so let me do this. What do you cube in order to get 27y to the 6th? That's the question. So now that I understand the question, I can see that I would have to cube, do you know it? 3y squared. Yeah, because 3 cubed, 3 times 3 times 3 is 27. Y squared cubed, you would multiply these two powers by the power rule for exponents. 2 times 3 is 6. So this is definitely the term that you would have to cube in order to get 27y to the 6th. So 3y squared goes there. Now this is really important because if the binomial factor is wrong, chances are the trinomial factor is going to be wrong. What I put first here is the square of 10x. The square of 10x. Now you have to square 10 and you have to square x. That's going to give you 100x squared. What goes in the middle is the product of 10x and negative 3y squared. 10x, or actually not negative, excuse me, I already determined that the middle term is going to be positive, right, by SOAP. So just focus on 10x and 3y squared. Multiply them together and you get 30xy squared. The last term is the square of 3y squared. Be careful, square 3 and square y squared. That will give you 9y to the 4th power. And this is the complete factorization for this difference of two cubes. Here's our last example. 9n to the 6th power plus 9,000 n cubed. What I would invite you to do is to pause this video now, pause the lesson, and give this a shot. And I want to give you a hint. I kind of want to point you in the right direction. Please don't forget that factoring out the GCF is always the first step. All right, go ahead and pause the lesson here and give this a shot. Okay, I hope that you realized that the GCF is 9n cubed. So I'm going to factor that out first. 9n cubed from both of these terms. That leaves me with n cubed plus 1,000. Okay? This right here is the product rule. This term times that term, you would end up adding these exponents, right? That's the product rule. So if you distribute back inside, you will get this original binomial back. 9n cubed times 9n cubed times n cubed gives you 9n to the 6th. You would end up adding your exponents. That's the product rule for exponents. All right, cool. Now you should see that this is a sum of two perfect cubes. So I hope what you did next is copy down the GCF and then break this up as a binomial followed by a trinomial. Same sign, opposite sign, always positive. N, you would have to cube n to get n cubed. You would have to cube 10 to get 1,000. The square of n is n squared. The product of n and 10 is 10n. And the square of 10 is 100. So this is the complete factorization for that binomial. Good job, everybody. All right, before we end this lesson, I thought it might be helpful to have a summary of factoring polynomials. Your first step is always to factor out the GCF if it exists, or I should say, it always exists. I should say, if it's other than 1, okay? The next thing you want to do is how many terms do you have? If you have 2 terms, these are your 3 options. Difference of 2 squares, sum of 2 cubes, difference of 2 cubes. Notice what is not on this list, a sum of 2 squares, because a sum of 2 squares, like we said earlier, is prime and never factors. If you have 4 terms, then you want to factor by grouping. And then when you have factored once or maybe even twice, make sure that that you're done. And what do I mean by that? Check each factor. Can they be factored further? All right. So we talked a little bit about that in this lesson. Make sure you have completely factored. And then you can always check your factorization by multiplying. If you multiply and you get the original polynomial back in return, then you have factored correctly. All right, everybody, I hope the previous 2 lessons have really helped you with factoring polynomials. I'll catch you later.